In progress.
Hey there, everybody. Welcome back. So far in chapter 6, we've looked at graphing lines through a couple of methods, and they all come from linear equations. In 6.4, we're actually going to start looking at not linear equations, but linear inequalities, and how graphing them is the same and different. So linear inequalities. So linear inequalities, we will have something like ax plus by is less than or equal to c, or we might have greater than or equal to, less than, one of those inequalities. So what we do is to graph these, we're going to, step one, temporarily replace the inequality as an equal sign. Or better, just pretend it's equal. And I'll show you both ways on the first problem. What I mean by that. And then step two, we're gonna align with the following differences from normal. If the inequality is strictly less than or greater than, we use a dotted line, not a solid line like we normally have been doing with linear equations. And then two, if the inequality has the equal sign, we use a regular solid line. Okay, and then there's one more thing that's the real big difference, is that for a linear equation, the answers are only on the line. For a linear inequality, they are on the line if it's got an equal spot, but they're not even on the line if it's less than or greater than. They will be either above or below the line. Everything above or below the line will be part of it, just only one side. So we're going to have to shade one side to represent that these are all the solutions. But to figure out how we're going to do that, what we're going to do is we're going to, for step three, pick a test point. Maybe I should use A and B here. So I had 1, 2, 3 for the main numbers. Pick a test point not on the line. And evaluate it in the inequality. So we pick a point that's just not on the line, somewhere else. Now we've got a couple options here. If the statement is true, if the inequality holds true, we're going to shade on the side of the test point. B, otherwise the other side will hold true. The other side has the valid region. So we will shade the side not including the test point. Okay. That's getting a little blurry. Let me hit. There we go. All right, so let's do an example here. This is not that bad. I can do 4 examples and have this probably in a 15-minute video. So example 1. Y is greater than 2/3 x minus 1. So we're going to graph this. Two, three, four, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4. Oh, one more thing I want to add to that last thing. Great test points. Pro tip for test points. One of the following is guaranteed to not be on the line. 0, 0, 0, 1, or 1, 0. At least one of these is not on the line. Well, how do I know that? Because they make a triangle. So at least one of them is not on the line. Pick one of them that's not on the line. 0, 0 is the easiest one to pick. So what we're going to do is we have a y-intercept of 0, -1, and a slope of 2/3. So 0, -1 is here. We're going to rise 2 and run 3. Maybe I'll add another dash here. Rise 2, run another 3. That's not 2. That's 2. And then I'll go down 2 and go left 3. Now, what I'm going to do, since I don't have an equal portion, I'm just going to make this a dotted line. Oftentimes people use dashes. I try not to do dashes because they look like asymptotes, but that's fine. That's the line. And now what I'm going to do is I'm going to pick a test point. Since the origin 0, 0 is not on the line, I'm going to test 0, 0. I plug in x for 0 and y for 0. Is 0 greater than 2/3 times 0 minus 1? I end up with 0 is greater than -1. That is true. So this is on the upper side of the line. I'm going to shade up here. What this means is any point up in this region works. Like I could try 2, 5. 2, 5 is up here. And I have 5 is greater than 2/3 times 2 minus 1. That's 4/3 minus 1. That's 5 is greater than 1/3. Also true. The closer you get to the actual line, the more questionable it gets. The closer it gets to being not true. On the line, it's actually not true. If 0, -1, I test the y-intercept. -1, is that less than 2/3 times 0 minus 1? -1, is that, I said less than, I meant greater than. Is -1 greater than -1? No, it's false. That's why we use a dotted line. The dotted line means the line is not included in the solution. Okay. All right, let's do a few more. Y is less than or equal to 3/2 x plus 3. And maybe I'll go a couple more up because it looks like we're going to be rising to the left or to the right. So my y-intercept is 0, 3. And my slope is 3/2. So rise 3, run 2. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. I have an equal portion, so I'm actually going to use a solid line this time, which means the answers are included. I'm going to test 0, 0, and I'll test 0, 3 just to show you that the line is included. If I plug in 0, 0, is 0 less than or equal to 3/2 times 0 plus 3? 0 is less than or equal to 3. That's true. So we are going to shade on the side that holds the test point. All the answers down here work. If I tested the actual y-intercept, 0, 3, 3 is less than or equal to 0 times 3/2 plus 3. I put those in the wrong order, but that's 3/2 in x. 3 is less than or equal to 3. That's true. It's not less than, but it's the equal part. So that's why we do a solid line. Every point on the line works, and every point below the line works in this case. That's how these work. We're going to do 2 more, and I want you to try to do them before I show you how. Okay, give 2x minus 5y is greater than or equal to 15 a shot. All right, I will assume you did. I am going to write this in slope intercept form. So I subtracted the 2x and then I divided by -5. Remember, divide by a negative and you have an inequality. You got to flip the symbol. This becomes 2/5 x minus 3. Hopefully you didn't forget that. So I have 0, -3, and I've got a rise of 2, a run of 5. Or I could go down 2 and go left 5. I'm also going to start doing the slope intercept method now. We covered it in the previous chapter, not chapter 6.3 on slopes. I have the y-intercept. The x-intercept is when y equals 0. 2x minus 5 times 0 is greater than 15. 2x is greater than or equal to 15. x is greater than or equal to 7.5. So I need some more dots. And that looks like they are all on the same line. That's good. It's a solid line because we have the equal portion of the inequality. I will test 0, 0. It's actually easy to test here. 0 minus 0, is that greater than or equal to 15? No, that's false. Since it's not greater than or equal to 15, I am going to shade on the side that does not include 0, 0. Okay. One more for you. Let's see. We've done, let's see. Y is less than 1/2 x. I don't even know if we covered this with slope-intercept method. What's the intercept here? This is like having a plus. So the y-intercept is 0, 0. It's the origin. My slope is 1/2. This is one of those problems where trying to do the intercepts and the slope doesn't help. We have a rise of 1 and a run of 2. Rise of 1, run of 2. Or I could fall 1 and go left 2. This does not have an equal portion, so we're going to use a dotted line. And you'll see that 0, 0 is now on the line, so I can't test 0, 0. I need to test a point not on the line, so I can choose 0, 1 or 1, 0. In fact, I'll do both. If I test 0, 1, I have 1 is less than 1/2 times 0. 1 is less than 0. That's false. If I test 1, 0, I have 0 is less than 1/2 times 1. 0 is less than 1/2. That's true. So you'll see one side works, one side doesn't. Top side was false. 1, 0 was true. We're going to shade downward. Okay. And that's why when I said one of these isn't on the line, pick one. 0, 0 is the easiest because there's no multiplication. I think I didn't show you what I meant by temporarily treated as an equal sign. So let me rewind to that 2x minus 5y equals 15. So I've been doing the pretend method that this is an equal sign. Now I'm not going to do the pretend method. I'm going to temporarily replace that with an equal sign. And I'm going to track over here what the symbol is. So now I can do the minus 2x. So that was step A, and I'm still greater than or equal to for step A. Step B, we divide by -5. I get y equals 2/5 x minus 3. I divided by a negative for step B, so I'm going to flip the sign. And now that I've got y by itself, I would graph this line like here, just picking the points, but not actually drawing the line yet. Then I'll put the inequality back in. Okay, that's kind of what I meant by temporarily replace it. I think it's better to just not replace it, and that way, because it's easy to forget to flip the sign right here if you temporarily replace it. In fact, it's easy to forget you had an inequality if you don't make a note of it and follow it. All right, that's it for 6.4. Peace.